Video is about problem 12.68. It's similar to 12.89, but this time we have an ideal gas. Okay, so the problem says a container holds 1.5 grams of argon at a pressure of 8.5 atmospheres. Okay, so how much is required to increase the temperature by 100 degrees Celsius at constant volume? Then the second part, part B, how much will the temperature increase if this amount of heat energy is transferred to the gas at a constant pressure? Okay, so let's talk about each of these. Hey, and let's write down what we do know. And this is going to be a little bit different than a solid or a liquid because we have a gas and we're dealing with gas inside of a container. All right, so our pressure is 8.5 atmospheres, and then our mass of argon gas is 1.5 grams. Okay, and then how much heat is required to increase the temperature by 100 degrees Celsius? So I'm going to write that down. Delta T is going to equal 100 degrees Celsius. So let me show you what I have written down. All right. So here's what we know so far. We know the pressure, which is 8.5 atmospheres. We know the mass of the air, 1.5 grams. And we know delta T, which is 100 degrees Celsius. Now, what's really incredible that I think most people don't think about is that air actually has mass. Um, and the air actually has quite a bit of mass, right? If you've ever been scuba diving, that's when I first realized it because a scuba tank is significantly heavier if it's full than if you've been scuba diving. Okay, there's a big difference. That air actually has mass, and that's what the pressure is caused by in the atmosphere. So when we're sitting here, there are um, thousands of feet of air on top of us. Gravity is pulling all that down, and so that actually creates pressure here on the surface of the Earth. So air has mass, and it's a pretty significant amount of mass. Video is the first part of the preparation for the final period. I will be going through chapter 11 and 12 and working out problems that are relevant for the final period. Exam 2 is available until tomorrow. Please fill it out as soon as you can, period. I'm also available to give you feedback on your attempts, period. If you use Discord to message me, make sure that you tell me your full name in a message, period. Not everyone uses their real name on Discord, comma, which is fine, comma, but I need to know who you are if you want me to look at your exam. Period. Thanks so much, period. I have started I have started building the final, and realistically it is going to be ready on Wednesday morning, period. I will also be releasing a series of YouTube videos about problems that are relevant to the final, period. Please watch those videos as they are important for the final, period. What is the moment of inertia for a hollow cylinder? Okay, guys, the next important thing is we need to read the problem, and it says, how much heat is required to increase the temperature by 100 degrees Celsius at a constant volume? Okay, so that means that our the pressure is going to increase in this situation, um, and our volume is not going to change. So to let me give you a little story to illustrate when this can happen. Back when I was in college, I worked at a coffee stand, and it was at a hospital. And I went to work one day, and I had a can of regular Pepsi with sugar in it, and it was sitting in my car. It was kind of between the seats. And I remember that the parking lot of the hospital was black asphalt, okay? Because we Americans love asphalt. We love to put black asphalt. And so in the summertime, the it's like 30 degrees hotter if you're standing on asphalt because it just absorbs heat and then it radiates it back at you. So you get the sunlight plus the energy from the ground. It just makes it 20 30 degrees hotter. So I left this can of Pepsi in my car in a black asphalt parking lot, and it was about at least 100 degrees that day, maybe 105 degrees. And so inside of my car, the temperature probably got to 130 to 140 degrees Fahrenheit. Now, this can of Pepsi is a fixed volume. And so as the Pepsi started to heat up, well, what happens? Uh, the vapor pressure goes up, meaning it starts to evaporate, okay, and there's more gas in there, okay. So the um, the pressure starts to build, okay, and the temperature goes up. As the temperature goes up, the pressure gets higher and higher. And let's just say this, that steam is much stronger than aluminum. An aluminum can is not that strong. And so after about, I don't know, but probably maybe an hour in the sun, I came back at the end of my shift at the coffee stand, and the can of Pepsi had completely exploded and sprayed the entire contents on the inside of my car. And so the inside of my car was covered with regular Pepsi full of high fructose corn syrup. Needless to say, I never completely got it out of my car, but I got a lot of it out. Well, let's look at the physics of what happened inside of the boiling can of Pepsi in my car on a hot summer day. This equation right here, it's PV equals uh, nRT, or PVT equals nR. Okay, let me show you a different way to write this equation, which I think will help you remember it. Okay, so we have that our pressure times the volume is going to equal N times R times T, where T is the temperature, P is our pressure, so T is temperature, P is the pressure, V is the volume of our container. Right? Sometimes you'll have a container that it can't change it can't change sizes. Okay? Like the can of Pepsi. It's got a fixed volume, and then n little n is the number of moles. Okay? The number of moles. We're going to talk about what a mole is. You hopefully already know a little bit about it. Avogadro's number is 6.022 times 10 to the 23rd. And this is a very important number because this is the number of particles in 1 mole. Okay, so Na is number of particles in exactly 1 mole. And a mole is something that is commonly used in chemistry, but we also use it in physics as well. Okay. And it's a unit of measure, just like if you get a dozen eggs. Okay. Um, so it's easy to talk about a dozen eggs. You can say, I'm going to go pick up 12 eggs from the store. Okay. Or you're going to get one mole of whatever the element is. Okay, so here's my carton of eggs. Okay, so imagine instead of this is 1 dozen eggs, just like with a dozen eggs, we can talk about the same thing with atoms. And if we're using atoms or molecules, we're going to talk about moles. And on the periodic table, so let's take carbon, for example. Carbon is number 6 on the periodic table. And that number up at the top in the corner, that tells you the number of protons. So here, let's look at carbon. So carbon is 6 on the periodic table, and then it's got this number down here, 1201. 6 is the number of protons. Okay, so this is the number of protons in that atom, right? So carbon, what is it made out of? A typical carbon atom will have 6 protons and 6 neutrons. Okay, so we'll make the protons turquoise. Okay, so these are we'll call these protons. And it also is going to make these ones this color. Okay, it's also going to have a number of neutrons. We'll make these solid ones here. Okay. And most atoms have protons and neutrons, so we'll have, oh, that wasn't a very good drawing. Let's do a different one. Okay, so we have, that was just kind of confusing. Okay, so we're gonna have, uh, yeah, I don't know how they kind of look. They're kind of distributed like this, maybe. I don't know what it looks like. It's kind of like a blob sort of in the nucleus. Okay. So we have 6 protons and 6 neutrons, okay? And um a mass of a proton and a neutron is about the same. And so this number here, 1201, this is the bridge between the microscopic and the macroscopic. So Avogadro's number is the bridge between the macroscopic and the microscopic, okay? And now, oh, let's draw the rest of the picture of our carbon atom here. We've got 6 protons, 6 neutrons, and we also have 6 electrons. Okay, and our electrons here. Okay, so we got 6 electrons there. Okay, so this is our carbon. This is our carbon 12. Yeah, so this is carbon 12. Okay, has 6 electrons, 6 protons, and 6 neutrons. Now, hopefully, you know that the number of protons is always equal to the number of electrons, right? So, um, those there's always the same amount. Basically, if an atom is missing an electron, it's going to pull an electron from somewhere else, which could be maybe another atom. Okay, so even if it has to share an electron, an atom that's missing an electron is hungry for another electron. Okay, and I know I said we were going to talk about this problem. We're going to get there eventually, but we gotta talk about this stuff because you need to know what these equations are talking about. Okay, so this is what Avogadro's number is. Okay, so if we have 12.1 grams of carbon. Okay, if we had this much carbon, okay, that would be 1 mole of carbon. Okay, now this would be for individual atoms. Okay, but we can also have moles of oxygen. Okay, let's talk about a mole of oxygen. Now, oxygen never exists by itself, usually. It's very rare to just have a single oxygen atom floating around. If you have oxygen in the atmosphere, it's always O2, okay? Most gases just they exist in a diatomic molecule. Okay, so let's look at the periodic table here, right? And we can see that here's oxygen. Okay, so here's my oxygen, okay? And it's a big O. And then up here we have 8, and down here we have 16.00. Okay, so what we can say from this is that oxygen has 6 protons and its molar mass is 16 grams, okay? Um, or its atomic mass is also 16 atomic mass units, okay? But oxygen never ever just hangs out by itself. It's always O2. Okay, so that means that there's always two oxygen atoms. It's very hard to just get pure oxygen. You can do it in a lab. You have to run a huge current, and then you can break apart this bond. Very difficult to do. Whenever you encounter oxygen in your life, it's always going to be O2. So the molar mass of oxygen, okay, there's 2 oxygen atoms, and so we just double the mass here. Okay, so this would be 32, um, 32.00 grams per mole. I learned something new today. Uh, the amount of energy it takes to explode a can of Pepsi, it's about 50 joules. You can blow up a can of soda with sugar in it. Thanks for watching this video. There will be more videos to follow. The other constant that we're going to need to talk about is Boltzmann's constant. Okay, this is another very important constant that we're going to use a lot. Okay, and Boltzmann constant is equal to 1.3806649 times 10 to the minus 23 joules per Kelvin. And this is a very important concept that we're going to use to relate the thermal energy in a gas to a gas's kinetic energy. Okay. And um and we're going to use specifically this equation, and I think this is the equation we're going to use to solve this problem, which is thermal energy is equal to 3/2 times N times Boltzmann constant times T. And N is uh, the number of atoms that we're dealing with. Okay. So this is the number of atoms that we're dealing with in a closed system. So let's go back to the Pepsi experiment here. I strongly recommend not doing this experiment. Leaving a can of soda full of sugar in a hot car on a sunny afternoon, because if you did that in St. Louis, you would have a very similar result. Your car would be covered in Pepsi. Okay, so here's my can of Pepsi. All right, full sugar Pepsi. Let's draw the Pepsi logo here. Yay, Pepsi. All right, we got some Pepsi here. Mmm, so good. I don't really drink Pepsi, but it's pretty good. Okay, so here's our can of Pepsi. Okay, and let's imagine that our Pepsi, okay, and we're gonna talk about really the volume that we're gonna talk about is just up at the top here. Okay, so up at the top of my can of Pepsi, it's full of liquid. Okay, but uh, each can of delicious Pepsi has a little bit of room at the top. Okay, there's a little bit of air in there, right? And so it's just right up here at the top of the can of Pepsi. And I'll draw, let's say that all the little gas molecules in here, we'll draw those in pink. Okay. So imagine these little molecules are zipping around in here. Okay. And the volume can't change as long as my can of Pepsi uh is intact. Okay. So this is like a fixed volume. Okay. You can also do this by throwing a can of beans in a fire. Also, please don't ever do that. Uh, because you will be covered in scalding beans and there will be metal shrapnel. Okay, but if you throw a can of beans in a fire, it will explode. Just like if you leave Pepsi in a hot car on a sunny day, it will explode. Okay, so we're talking about a fixed volume up here at the top of my can of Pepsi. Okay, and for this volume. Okay. There are a certain number of atoms or molecules. Okay. So this is number of particles. We'll say number of particles. Number of particles. And they're bouncing around. Okay. So let's zoom in here to the top of the can of the Pepsi. We're gonna zoom in here. I'm gonna draw a giant can of Pepsi down at the bottom of the page. Yes. Here's my can of Pepsi. Okay. We have the liquid Pepsi down here in the bottom. Okay, so here's my liquid Pepsi. The can the can is full of liquid Pepsi. And my cat is asking for some what? Well, let's imagine we have one Pepsi molecule. Okay, and before the sun starts shining, this thing is flying around. It's got some kinetic energy. It's gonna bounce off the walls. Okay, this thing is just kind of bouncing around. And it's not gonna do anything. It's not gonna spray boiling Pepsi on your car. Okay, but let's say when you shine the sun on your car. Okay, these atoms get a huge amount of thermal energy. Okay, and their kinetic energy is very high. And so they go very, very fast. I mean, these Pepsi molecules are zipping all over the place. Okay. Now, the pressure inside of a container comes from the air molecules hitting the sides of the container. So, what does that mean? Well, the hotter these molecules get, the more kinetic energy that they have. And they start striking the surface of this container with more and more force. Okay. And I drew them a little bigger because yeah, the electrons on the atoms are getting more excited and they're also getting more, their path length goes way up and they have very high kinetic energy. Okay. And in the book, okay, it talks about this equation right here. This is related to the kinetic energy. Okay. Um, Another way we can write this equation is the thermal energy. The thermal energy is equal to the number of atoms times the average kinetic energy of those atoms. Okay. And it's the same thing. A way to calculate that is right here. Okay, so this is how we get the kinetic energy of our gas molecules. Okay, so what you could do is you could say, okay, what is the kinetic energy of my gas? I can just set these two things equal to each other. I'm going to say, okay, the number of atoms times the average kinetic energy is equal to 3/2 times n times Boltzmann's constant times T. Okay? Now, um, I'll talk about this equation a little bit here, but the number of atoms cancels out. Okay? And this is some really cool physics because what this is saying now, okay, is that the average kinetic energy of a Pepsi molecule in my car on that hot summer day that my wife never let me forget because my car was literally sticky for years, okay? So the kinetic energy is equal to 3 half times KB times T. Now, where did they get this equation? Okay. How did we come up with this? Okay, because this is a very useful equation. Okay, we can do other things here. Let's say we want to find, well, okay, these molecules are zipping around in here. How do we find what their velocity is, right? How do we know how fast these things are actually moving? Okay, well, this is really cool. Okay, we're gonna say, all right, so this is equal to 1 half times m times v squared, because that's our kinetic energy. Okay, so this means it's gonna be our average velocity, and that's gonna equal 3 halves uh, times kb times t. Okay, well, guess what? Now we can solve for our velocity of a single gas molecule. Okay, so I'm gonna multiply both sides by 2 here. Okay, my 2's are gonna cancel here. All my 2's are gonna go away. Okay, I'm gonna divide both sides by m. Divide this side by m. Okay, and I'm gonna take the square root of both sides, and so I'm gonna end up with here, after a little bit of algebra, it's gonna be 3 times kb times t over the mass of one of these molecules. Okay? Um, so that's kind of an amazing result because this tells us what the velocity of those gas molecules are in terms of the temperature. Okay? So if I know what the temperature is, then my velocity is going to increase or decrease depending on the temperature. So back to this can of Pepsi. Okay, so when these gas molecules start moving around fast enough, they will hit the sides of the aluminum can with enough force to make it explode. Okay, and if you boil a can of Pepsi, it will spray Pepsi all over your car. All right, so I know this was a lot to talk about, but here is the equation that we're going to use to solve this problem. Okay. So we this is our thermal energy, okay? And so we can use this to say, well, um if we know what the temperature change is, okay, we can relate that to the amount of thermal energy here. Okay? So let me just say that again. The whole point of all this is if we know what the temperature change is of our gas in this fixed volume, okay? We can now calculate the amount of energy that that is going to take. Okay? All right. So we have our equation for this problem, which is good. It's always good to know what equation we're going to use. Okay, so where are we at here in terms of the problem? Because that's what we're trying to figure out here is we want to actually solve this problem. And we now have the equation to tell us how much thermal energy we need to supply to n number of gas molecules times Boltzmann's constant times the change in temperature here. So we'll call this delta T. Okay, here's the energy that we need to supply to our system. And remember, we're talking about a closed volume. Okay, so this is some container here that's full of ideal gas particles. Okay, and so these particles bounce elastically off the walls, and so here's the amount of energy that you need. But you're like, but Dr. Wisby, I, I have 1 point. What did it even say? Ah, yes, of course. I have 1.5 grams of argon. Okay, how many particles is that? How many particles is that? And what kind of question mark is that? Oh my goodness. Okay. Well, you know what? I'm so glad you asked that because now you have the ability. If I say I have 1.5 grams of argon, how many particles is that? I feel like I'm going to ask that on the test tomorrow. So I'm going to do this problem on the test. Okay? So this will be I'm gonna be yeah, this is gonna be on the this is going to be on the exam. So let's look at the periodic table because I'm making this video and as much as I love to hear myself talk, I think there needs to be a reason. So if you watch this video, your reward is that you are going to know how to solve this problem. All right, so here's the periodic table. We see that argon has an atomic number of 18 and it has a mass of 39.95. Okay? So here's its atomic number and here's its molar mass or atomic. This is how many atomic mass units it has. But this is how many grams 1 mole of argon weighs. Okay? All right, so let's go through this, guys. This is definitely going to be on the exam. I just know it. And I'm the one making the exams. Okay, so, all right, how do we figure out how many moles do we have? Okay, so here's our mass of argon. Okay, we have 1.5 grams. 1.5 grams. Okay, now we're going to divide this. Okay, um, by the by the molar mass. So this is going to be 39.95 and this is grams per mole. Okay, so this is going to be and this is going to give us the N, the number of moles. Okay, little n here. Yeah, n is the number of moles. Okay, this is the number of moles in our problem. All right, so let me get out my calculator. Okay, so we got our calculator here. Can't really see it, but that's okay. I'm gonna hold it at this angle. All right, so we've got 1.5 divided by 39.95. Okay, all right. So now we know the number of moles. That seems a little low. Okay. Yes. Okay. So 1 mole would be 39.95. And so we are gonna have let's write this down here. I'm gonna write this down. Okay. So N, the number of moles is going to be 0.0375 469 moles. Okay, we found the number of moles, and this is a very, very important equation. It's yes. Okay, so I'm gonna give it to you now. N, the number of moles equals N, the number of particles divided by Avogadro's number. Okay, so here we go. Write this down. This is muy importante. N is the number of moles. N is the number of atoms or gas particles. Atoms or particles. And Na is Avogadro's number. Avogadro's number. And Avogadro's number, of course, right? Na equals 6.022 times 10 to the 23rd um atoms or particles. Now, why do I keep saying atoms or particles? Well, if you have a diatomic gas like oxygen, okay, then it's the number of molecules. If you have a gas like argon, argon is not a diatomic molecule, it is a single atom. So argon is a monatomic gas, okay? And how do you know if it's monatomic or diatomic? Diatomic would be like oxygen, right? Oxygen is always O. It's always O2. Same thing with nitrogen, okay? Nitrogen also is always exists in it would be N2, right? Same thing with chlorine or sulfur. Okay, the only monatomic gases are helium, neon, argon, krypton, xenon, and the other ones here on the periodic table. Okay, those are the monatomic gases. So we have argon, and so that's an important clue about how many moles that we have. Okay. All right, so we know that argon is monatomic, and we're trying to figure out, well, how many gas particles do we have so we can use this equation up here. Okay, so um, now I'm gonna get N. Okay, did I already find N? Oh, I found N the number of yeah, that's the number of moles. Okay, I took the molar mass and I divided the mass of the argon that we had by its molar mass. Okay, this tells me N, the number of moles. Okay, now, so what I'm going to do here is I'm going to say big N, okay, is equal to little n times big N, Avogadro's number. Okay, so I'm going to take the uh, I'm going to take the number of moles and multiply it by Avogadro's numbers, and that's going to tell me how many particles I have. Okay, that's what I want. I want the number of particles. Okay, so I'm going to take my results and I'm going to say, I'm going to go up here actually. So I don't like to just multiply it by the answers. I want to keep everything here in the same line so that I can go back and I can read it. So I'm going to type in Avogadro's number here, 6.022 times. Here, I'm doing scientific notation. 10 to the power of 23. Okay. And what do we get here? Aha. Okay, so this is the number of particles that I have here. Okay, so it's 2.261 times 10 to the 22nd. That's how many atoms I have. Okay, I'm gonna write that down here. Okay, so I have N, which is gonna equal 2.261, and I'll write down these other numbers. 0763 times 10 to the power of 22. That is the number of atoms that I have. So we have just figured out 1.5 grams of argon gas has 2.26 times 10 to the 22 argon atoms. And we'll say this is argon atoms. Boom. Okay, now we can plug all this in here. And it's getting a little crazy on my calculator. So I think I might throw this one into MATLAB. But you're like Dr. Wisby, I don't get to use MATLAB on the test. You know what? You're right. Okay, we'll put it all in here. You know what? I'm gonna go back up to this line. Okay, I'm gonna keep everything here. I got 1.5 divided by 3.95 times Avogadro's number. Okay. And then what do we got over here? All right. We figured out what n is. Okay, that's what we got right here. So now we need to add Boltzmann's constant. We'll put in the 3/2 times 3/2. Okay, this comes from the fact that it's an ideal gas. And we got to multiply by Boltzmann's constant, KB. KB, not Kobe. Okay, so we're gonna put this in. Okay. Boltzmann's constant, I wrote it down over here. It's 1.380649. I'm gonna keep all the digits in. Oh, and look what I did. Oh my goodness. I put an extra decimal there. I'm selling. Okay. 649 times 10 to the 23. 10 to the power of 23. Okay, what do I got here? And the temperature change, delta T. What did the problem say? The survey says, all right, way back when we were talking about this problem. Oh, it's 100 degrees Celsius. It's 100 degrees Celsius. Okay, we're gonna put in that's delta T times 100. Okay, let's just review here. I'll press enter. Okay. I got some kind of weird answer here. All right, what do we got here? 4.68 times 10 to the power of 47. That is not right. I don't know what the heck. What did I do? All right, I feel like I forgot. Now see, the beauty of this is I know that this answer is wrong, okay? Because that answer doesn't make any sense, okay? It should be a number of joules. I'm thinking maybe a few hundred or a few thousand. Okay, I don't know what happened here. I'm gonna go back and I'm gonna look at this. Okay, I have 10 to the power of 23. Now the other one here, okay, oh, there it is. This was supposed to be, oh, first of all, okay, right here. This was supposed to be the power of 22. And then the ideal gas constant is the power of minus 10 to the 23. Okay, see, I kept all this in here. And see right here, this should be minus 23. So I'm going to press second insert. I'm going to try and put in a minus sign here. Boom. It did. Oh, it took it. Okay. Wonderful. All right. And now, am I still in insert mode? Oh, jeez. I don't know. Oh, no, I had. Okay. Let's press enter here. Okay. 46.8. That seems a little bit more reasonable. All right. Let's go through the math one more time just to make sure that we got it all. Okay, I think I had it, but I forgot to push record. So we put the numbers in here. We ended up getting 46.8 joules. We use this equation here. The thermal energy required to raise the temperature, that's delta T, is equal to 3 halves times n, the number of particles, times Boltzmann constant times the change in temperature. Okay. Um, right here, we used the fact that argon has a molar mass of 39.95. Okay. So then we said, all right, how many moles do we have? Okay, because we need to find out what N is. I don't know what N is. I don't know how many particles there are in 1.5 grams of argon, so we need to figure it out. Okay, we can get it from this equation right here. Okay, the number of moles is equal to the number of particles divided by Avogadro's number. Okay, and this mass here on the periodic table, that is the mass in grams of this element per mole. So 1 mole of argon weighs 39.95 grams. Okay, so we said we have 1.5 grams of argon divided by the molar mass, 39.95 grams per mole. Okay, that gives us 0.0375 moles. That's the number of moles that we had. Okay? Then we use this equation right here. Okay? The number of moles equals the number of particles times Avogadro's number. So I multiplied both sides by Avogadro's number. Okay, so we had little n times Avogadro's number. Number of moles times Avogadro's number tells us the number of particles. Okay, so we had 2.26 times 10 to the 22nd argon atoms. Okay? So to get the thermal energy then, okay, it's 3/2 times the number of particles, N, 2.261 times 10 to the 22nd, times the ideal gas constant, 1.38 times 10 to the 23 joules per Kelvin, times our temperature change. So 100 degrees C. This is how much the temperature of our gas changed in this enclosed container. Okay. That gave us a very reasonable answer of 46.8 joules or 47 joules. When I first calculated this, I forgot the minus sign here on the ideal gas constant, which of course gave me an answer that was times 10 to the power of 46. That doesn't make any sense. I don't know if even the sun has that many joules in it at any given time. That's probably enough to melt the planets. I haven't done the math, but it seems a little bit high. Anyways, uh, back to my can of Pepsi here. So 47 joules is the number it would take to explode a can of Pepsi. Wow. I learned something new today. Uh, the amount of energy it takes to explode a can of Pepsi, it's about 50 joules. You can blow up a can of soda with sugar in it. Thanks for watching this video. There will be more videos to follow.
Thank you, like and subscribe down below.